Welcome, everyone, back to the Langtangen Seminar 2026. We're very happy to have with us Professor Matthew Colbrook from the University of Cambridge today. Matthew is an associate professor in the Department of Applied Mathematics and Theoretical Physics. He was previously a junior research fellow there, but also as a FSN de Paris fellow at the Coopman Supérieur in Paris. Matthew is interested in a lot of things, in particular infinite dimensional spectral computations, Koopman learning and data-driven dynamics, neural networks and optimizations, and many others. He's won many early career prizes, including SIAM Data Science Early Career Award, Leslie Fox, second prize, SIAM the Prima Prize, and his book on infinite dimensional spectral computations will be appearing this August from Cambridge University Press. So Matthew, very happy to have you today, and the floor is yours.
Thank you. Thank you for the introduction and the invitation. Okay, so I'm going to be talking about data-driven Koopman methods from a numerical analysis point of view, and I'm going to be focusing on three things, so spectra and forecasting. So we'll see how those two are related. And then towards the end of the talk, I'm going to give you a bit of a brief glimpse of open challenges that people are working on in the area as well. So I will put these slides up on my website, so you can get hold of them after the talk as well, and there's a link here as well. Okay, so hopefully this all works. There we go. What is a Koopman operator? So when you see this for the first time, it's a little bit weird, so I thought I'd go through it reasonably slowly. So suppose that you have a discrete time dynamical system. So you have a state space, capital X, the state, little x, will live inside the state space, and the dynamics are governed by some continuous function f. So the state at time n plus 1 is f of the state at time n. Now, in general, f can be nonlinear. Okay, so this is sort of the classical viewpoint. And then in the 20th century, let me just hide this panel. There we go. Koopman had this idea of looking at, rather than the dynamics of the state, how observables of the state act with the dynamics. Okay, so observables are functions from the state space to the complex numbers. Think of this as, for example, measuring the temperature at a particular point of this phase space or something like that. And he looked at something called, which is now called the Koopman operator, which is composition with this function f. Okay, so k is this operator, g is this observable. So kg is another function of the state, and it's given by g of f of x. Now, even though this original f is in general nonlinear, I mean, x need not even be a vector space, this operator here is linear. And you have to be a bit careful about which observables you allow, so which vector space K acts on. For the first part of this talk, I'm going to look at L2 functions. Okay, so there's going to be some positive measure omega on the state space that I won't really dwell on, and then G will be inside this L2 space. So the point of this Koopman operator is that it observes G one time step forward. Okay, so there's two very nice papers. Von Neumann got involved as well. So the goal was to try and do for classical dynamics what he'd done for quantum dynamics using operator theory. And then we move into the 21st century, and lots of people are interested in using data to study various things. So in our context, this F that governs the dynamics is now unknown, or it might be too complicated to analyze directly. And instead, what we have available to us are samples of F in the form of trajectory snapshots. Okay, so these are X in blue and Y in green, where Y is f of X. And we have a finite number, m equals 1 to capital M. And the goal for the first part of this talk, at least, is to try and compute the spectral properties of this operator that's lurking in the background from this data. Okay. So why might you want to do this? Why is it useful to study the spectra of such a weird looking operator? So here I've written down the action of the Koopman operator n times on an observable G for an initial condition x naught. It gives you G of xn. And this means that if you find what we call a pseudo-eigenfunction, so if G is almost an eigenfunction in the sense that kg minus lambda g, the norm of this is less than some tolerance epsilon, then G of xn, so this is evaluating the observable n time steps forward. What is this? This is applying the Koopman operator n times the G and evaluating at the initial condition. And this is lambda n, lambda to the n, times the original condition. okay, plus some error term that you get from only approximately satisfying kg equals lambda g. Now, the O notation here means in whatever norm you're working in our case, the L2 norm. But the important thing is that this grows linearly with n, and as epsilon gets smaller, as you get more and more accurate approximations here, you have a longer time period where this is a good approximation. Okay, so here's an example. This is for the Lorentz system on the Lorentz attractor. So for this example, and I'll show you a picture of the spectral measure towards the end of this talk, there are actually no eigenfunctions of the Koopman operator except constant functions. Okay, so a constant function is always an eigenfunction. K of g is equal to g because it doesn't evolve or change as you compose with the map F. But we can still get approximate eigenfunctions, okay, which behave in this sort of coherent way according to the power of the associated approximate eigenvalue lambda. So this is a chaotic system, okay, so it's very difficult to predict or get these features, but you can still drive this epsilon down close to zero to get these sort of patterns that capture some sort of oscillatory behavior within the system. Okay, so you should think of this Koopman operator as trading a nonlinear, typically finite dimensional dynamical system for a linear but infinite dimensional operator because we're acting on an infinite dimensional space, this L2 space of observables. And one of the sets that we're interested in computing is the set of Z, or the set of lambdas here, where there exists an observable normalized to have norm 1, where kg minus zg is less than or equal to epsilon. So this is called the approximate point pseudospectra, a bit of a mouthful. If you've seen pseudospectra of matrices, just think of it like that. But this is a set, a sort of a spectral set in the complex plane that's capturing the approximate eigenvalues where you can get this type of behavior. Okay, so if you can compute these pseudo eigenfunctions, or in other words, compute spectral properties of the Koopman operator, this in turn allows you to do things like forecasting. Okay, so for example, let's suppose we find a collection of such observables. So you can think of these as sort of verified approximate pseudo eigenfunctions. And suppose that you can expand the state in terms of these observables. So now I'm thinking, for example, if the state space is a subset of Rd, okay, and then I'm vectorizing the previous equation. If I can expand in terms of this basis, then I can forecast, okay, because if I want to evaluate n time steps forward, this is the same thing as applying the Koopman operator n-fold to this initial approximation plus some error term, and I know how these behave according to these eigenvalues. So you can think of this as an approximate nonlinear separation of variables through a linear operator. So you're trying to split the signal or the dynamics of the system into these coherent features, and they might oscillate or grow in time according to the approximate eigenvalue lambda. So that's really the motivation of this Koopman operator. You somehow split up this complicated nonlinear dynamical system into simpler parts that are behaving in a predictable manner. Okay, and you do this by lifting to this infinite dimensional space of observables. Okay, so approximating spectra, I thought I'd give you a little example to show you what can go wrong. So the Koopman operator is typically infinite dimensional. And if I hand you an infinite dimensional operator, the first thing you want to do is maybe truncate it or discretize it to a finite matrix and compute eigenvalues. So here's something called the shift operator, which is acting on the Hilbert space little L2 of Z. So think of this as acting on Fourier coefficients of a periodic function. And it does this by shifting the coefficients back one according to this sort of infinite Jordan block. Okay, this operator is really nice. The spectrum is the unit circle. It's a unitary operator. The spectrum is stable. And there's in fact no eigen vectors of this operator. Okay, so when you go to infinite dimensions, it's no longer the case. The spectrum of the operator just consists of eigenvalues. You have to be a bit more careful. But if you're thinking about dynamics, if you're applying this operator to a vector, you preserve the L2 norm. Okay, so it's unitary, gives rise to unitary evolution. Now, if I hand you this infinite matrix and you try and compute its spectral properties, numerically, you might take a finite truncation of the operator. Okay, so we would call this the finite section method. If you take a finite section of this infinite matrix, you get a Jordan block. And this is sort of the bad guy of numerical linear algebra. So if you've ever sort of tried to compute with matrices and run into Jordan blocks, you're told not to really proceed or try to come up with a different method. They're very badly behaved. So the spectrum of this matrix is zero. The spectrum is unstable, in fact, exponentially so in the dimension n. You've got discrete spectra and you've got nilpotent evolution. So you've broken all of the nice properties of your underlying operator. And this isn't just an academic example. A lot of Koopman operators that you run into in practice can be built up by sort of operators that behave a bit like this shift. Okay, so when you truncate to a finite approximation, you're going to lose something about the operator. Okay, so really a lot of this talk is about how to control these errors. How do you control these truncation errors, these closure errors? So the problem here, of course, is that if I take a truncation, I'm missing a one up here, right? So which corresponds to how the finite subspace that I'm looking at interacts with the whole other subspace. There's a closure issue. You don't have an invariant subspace of this operator. Okay, so how do people actually compute spectral properties of Koopman operators in practice? Well, the most common method is something called extended dynamic mode decomposition. So there's some papers here. These are sort of the three main papers. But essentially, all this is a Galerkin approximation of this operator. So if you've done things like finite elements, you'll notice that it's exactly the same type of idea. So you start off with a basis of observables, psi1 up to psi n. And then to approximate your operator, you have to compute two types of inner products. This inner product between the basis functions themselves, corresponding to a Gram matrix, and an inner product where you're taking the Koopman operator acting on this psi k on the left. Now remember, all we have access to are these snapshots, this data. So what we do is we treat the x points, these blue points, as quadrature points with quadrature weights Wm. I'm not going to go into the details of how you select these. I can if people are interested after the talk, but you can develop a convergent theory for them. And essentially what you do is you build up this quadrature approximation of the inner product here, and this gives you this type of structure here. So here you have this psi x matrix, which is just the basis or observables evaluated at the blue points, the x points. And then if I want to apply the Koopman operator to psi k here, because the Koopman operator just composes with f, and I know that y is equal to f of x, it's very simple to do this without needing access to the function f. Okay, so I only need to replace these x points by these green y points and this psi x by this psi y. Once I've got these two matrices, I form my Galerkin approximation as follows. So if we're going back to this picture here, you should think of this as the analog of this matrix here. So you're truncating to a finite dimensional subspace spanned by these observables. Okay, so far so good. Now, if we try and do this on an example, often it doesn't convert, so you don't get good spectral properties because of the truncation error. So here's an example, the Duffing oscillator. So this is a system of ODEs on R2, and I've sampled this system to time step 0.3, okay, to get a discrete time dynamical system. For my observables, for my basis functions, I'm going to pick Gaussian radial basis functions. This is the typical choice that people use. And then to approximate my inner products, I'm going to use Monte Carlo integration with about 50,000 quadrature points. Okay, so this is large enough to not affect the results. So this alpha here that you see in this ODE, this is a dissipation parameter. So if I set it to 0, the system is actually Hamiltonian, and the Koopman operator is unitary. So its spectrum is a subset of the unit circle, and in fact, in this case, is the whole unit circle. Here I've got blue. These are the EDMD eigenvalues. So if we go back one slide, that's the eigenvalues of this matrix here. And in color, what I've shown is this approximate point pseudo spectra that I've computed using a method I'll describe in a couple of slides' time. So you should think of this as a way of detecting whether the blue guys are good or not. So we see that we get a lot of spurious eigenvalues inside here, and this is known as spectral pollution. So this occurs because we're going from an infinite dimensional Koopman operator and projecting onto a finite dimensional subspace, and we lose something in the process of doing that. And there's a similar picture if we turn on alpha, so we add dissipation. Again, we get a lot of spurious eigenvalues. And then you can plot the maximum error of these eigenvalues against the matrix size. How many basis functions do you use? And you see that you don't get conversions. Okay, so can we fix this? Can we somehow control the error when we go from this left infinite dimensional operator to this right finite approximation? And the answer is yes, we can. So if we go back to the EDMD matrices, we can think of this as sort of, in terms of these colors, these blue and greens. We have blue, blue corresponding to the ground matrix. We have this K1 matrix, which is blue, green. And then we can take the adjoint, so we can put the K on the other side to get green, blue. And then if we look at this, okay, you can kind of think of these as correlations. We're missing one particular correlation, which is green, green. So this is where you have the Koopman operator acting on both sides inside this inner product. Okay, so we've just looked at the color codes and we've come up with some other matrix. Why is this useful? Well, suppose that you have a candidate pseudo eigenfunction, okay, and a candidate approximate eigenvalue. So you want kg minus lambda g, the norm of this, to be small. Well, you can measure the size of this norm. Okay, so you square the norm, you get this inner product. You could represent this in terms of the basis, vectors like this. Now I have these three matrices, G, K1, K2. And I can show that as m goes to infinity as my quadrature converges, I get this residual squared exactly in terms of these finite matrices. Okay, so I can compute an infinite dimensional error bound using finite matrices by considering this additional correlation. Okay, so a really simple idea. And what you're essentially doing is you're checking whether this pseudo eigenfunction is behaving when like it should when you march forward in time. Okay, so that's why you're looking at these sort of forward-time correlations. Okay, and this allows you to compute the spectra. So for example, if we go back to our Duffing system, we just, sorry, go back here very, very quickly. If I minimize this over lambda, I get exactly these color plots here corresponding to the approximate point pseudo spectrum. And I can, in fact, use this residual to develop an algorithm that approximates the approximate point pseudo spectrum and converges as epsilon goes to zero. And this is what you're seeing over here in this plot on the right. Okay, so you can clean up truncation errors of these Koopman operators by using this additional green-green matrix. Okay, so if you forget everything that I've talked about so far, just think of this this picture here with green-green and think of it as a way to control the subspace truncation error of the Koopman operator. Okay, so we can turn this into a theorem. If you want the exact statement of the theorem, then you can look at this paper here that's available on my website. So what I'm going to do is consider the space of observables L2 x omega. So think of these as observables with finite energy. And I can use this residual to construct an algorithm that depends on n and m. So remember, n is the size of the dictionary or the basis number of basis functions. M is the number of quadrature points. And I can converge in a double nested limit to this approximate point pseudo spectrum for all systems. So of course, there are some assumptions on the systems, but they're very minimal, and I don't want to get bogged down into that. Okay, so we have a way of getting this set. So remember, this is the set when we were talking about the Lorenz attractor that gives us those coherent features. And now we can ask the question, well, we've got a double limit here. We have to take m to infinity, then n to infinity. In practice, of course, we want to maybe choose n depending on m. Can we do better? Can we get a single limit result for approximating this set? And this is where it gets interesting as well. you can actually show that for a lot of classes of systems, you can't. So you can build adversarial dynamical systems that will screw up algorithms and stop them from converging when you're approximating the spectral properties of Koopman operators. So here's one such result. So I'm taking continuous functions on the unit closed unit disk in the complex in R2, and I'm restricting myself to measure preserving and invertible systems. I can even make them smooth if I want. And these assumptions imply that this Koopman operator is unitary. Okay, so you've got a very nice restricted class of dynamical systems with Koopman operators with good properties. And of course, if I restrict the class, when I prove an impossibility result, that makes the impossibility result stronger. And I'm going to be very generous to my algorithms. I'm going to allow them to sample at any point in this disk f to any accuracy that they want. Okay, so think of this as like a perfect measurement device. You can sample, you can get as many snapshots as you want, and you can get them to as high accuracy as you want. So you can drive down the error of the measurements to zero. And even then, you can't do it. So here's the precise statement of the theorem. There does not exist any sequence of deterministic algorithms, gamma n, using this measurement device that converges in a single limit to this approximate point pseudo spectrum for all f in your set here. Now, I've used a little n to index the algorithm or sequence of algorithms. N here can index anything. It's not tied to truncation size or the amount of data or anything like that. It's just a sequence of algorithms. So this is a very general result. It's universal, so this allows any type of algorithm or computational model. So it's sort of an intrinsic analytical barrier to computing the spectral properties of these operators. And you can also prove a random result as well. So if you allow, random sampling of trajectories or stochastic gradient descent to train a neural network or whatever, you can prove that you can't get convergence with probability greater than 1/2. Now, for the sake of time, I'm not going to go through the proof of this. The proof is quite fun as well. So I have a few extra slides at the end in case anybody wants to discuss it in the discussion time after the talk as well. Okay, so we have a positive result. You can do something in two limits. Okay, you can overcome the spurious eigenvalues or that spectral pollution. And then we have a negative result saying you can't beat two limits. You have to use two limits. You can't do it in a single limit. And we can use this to actually start to classify the difficulty of computing these Koopman operators. And this is something I've recently got interested in. So, for example, if you want to solve a computational problem or compute the spectrum of this Koopman operator, and you have an algorithm that converges and is for any given n is bounded at the error is bounded by 2 to the minus n, you think of this as full error control. Okay, so this is delta one. This never really happens in practice. The SCI is the fewest number of limits needed to solve a computational problem. Delta n plus 1 are problems where the SCI is less than or equal to 1. So if I go back here, this is a delta 3 classification saying I can converge in two limits. This is a classification that's saying I don't live inside delta 2, so I cannot converge in a single limit. And likewise, you can consider convergence from below or convergence from above if you want to get verification. So for example, if you had a sigma 1 classification for computing the spectrum of a Koopman operator, this would be convergence. And you also know that anything in your output in your algorithm is guaranteed to be close to the spectrum of the Koopman operator and vice versa. So this allows us to start to place different dynamical systems in this classification theory. So for example, if we look at measure preserving systems, so remember those are the systems for which I had a negative result on the disk. I can prove that they live in sigma 2 here. Similarly, if I can control the variability of f through a modulus of continuity like here, I can get a delta 3 limit and in fact a pi 2 classification. So these require two limits. And then you can show that if you drop all assumptions and just assume that the map is continuous and you don't know anything else about the system, you need three limits to compute the spectra of these Koopman operators. Okay, so there's a very interesting connection between the flavor of the systems that you're looking at and how hard they are to how hard it is to compute the spectral properties of these Koopman operators from data. Okay, so let's just go back to this theorem here, this is, of course, a negative result. And you might ask the question, is there some way around it? Okay, and there's this sort of advice from Peter Lax that if you're stuck, then it's good to try. So the trick of the successful mathematician is to turn the question being asked into one he knows how to answer. Now, in the previous impossibility theorem, it's saying that we can't do something. So it's a rigorous lower bound on the difficulty, but we can change the question, okay? And then the result might change. So we can perform this trick by changing the space of observables. So far we've been dealing with L2 spaces. I'm now going to change to reproducing kernel Hilbert spaces, okay? And this is a rapidly growing area within inside the community on Koopman operators. So if you don't know what an RKHS, a reproducing kernel Hilbert space, is, don't worry. This box summarizes everything you need to know to understand the talk. So all it is you take your state space and you consider a Hilbert space of functions so that the map from G to G of X, so remember G is your observable, your function, this is a bounded linear map for all X in your state space. Okay, so pointwise evaluation is bounded. Um, Now, if you're struggling to think of such a Hilbert space and you've studied PDEs, you'll have come across Sobolev embedding theorems. Okay, so those are saying that for Sobolev spaces of a certain regularity, it makes sense to take pointwise evaluations of the functions, and you can actually prove that they're bounded. Okay, so that's a classic example of an RKHS. Now, any RKHS is generated, by a kernel, which is just a map from X cross X to C. Now, because this is bounded, the Riesz representation theorem says that there exists a vector, which we'll call Kx, inside our Hilbert space. So G of X is the inner product of G and this Kx. And this kernel is just simply what happens when you take the inner products between Kx and Ky. Okay, so this is all you need for the next couple of slides. Now, why might you want to study such observables? Well, if we go back to our sort of goal of using these spectral information to forecast, if we have a bound in the norm of whatever Hilbert space we're working in, if it's an RKHS, this immediately leads to pointwise bounds, okay? Because this functional here is bounded. So this allows you to get forecast pointwise error bounds, which we'll see later on. You can also use them for very high dimensional systems using the kernel trick. So you can compute inner products by just evaluating this kernel function. There's actually a lot of fast methods for evaluating particular classes of kernels. And if you change the space, if you change the kernel, you're changing the Hilbert space, which is actually changing the operator, the Koopman operator. So remember, in infinite dimensions, the operator isn't just some big infinite matrix. It's determined by the space that you're working on. So you can actually tailor the Hilbert space to the particular dynamics that you care about. And this is where a lot of people like Igor Mezek are going at the moment. Okay, and we'll see in a second that this leads to fundamental possibility gains. So if I go back to this picture here, the situation gets easier. So why is that? Well, there's a very nice relationship between the adjoint of the Koopman operator and its action on these kernel functions. So K star, the adjoint applied to Kx, this is Kf of x. So if you look at the evolution of functionals instead of observables, you get this beautiful duality. And this allows you to get those three types of inner products. So the blue-blue, the green-blue, and the green-green without any quadrature. Okay, so you don't need to take m, the number of data points, to infinity. Okay, so you can evaluate this residual exactly without needing to take a limit. And you can find details on this in our recent preprint. So we can turn this into an algorithm to compute this approximate point pseudo spectrum. So we take this normalized squared residual here, which you can represent using these finite matrices. And we, over a grid of points, we minimize this residual, okay? So we fix lambda over this grid. So these are these zk, and we minimize the g here. And these give us our approximate pseudo eigenfunctions. Okay, so these epsilon pseudo eigenfunctions, sorry. Um, and then if you threshold these below a certain tolerance, okay, you have the following theorem. So you're always guaranteed to be inside this approximate point pseudo spectrum. And in fact, because you've coupled n, the size of the basis, and m, the number of data points, you can show that you converge to this spectral set in a single limit as n goes to infinity. So things get easier if you change the space of observables. So whilst the L2 case in the first part of this talk is sort of the classical ergodic theory setting of Koopman operators, if you change the space, things can become computationally easier. Okay, so before I tell you a bit about challenges, let me just show you an example of this in action. So here I'm going to take sea ice data over the Antarctic region over the last 40 years. So this is a monthly time series. And I'm going to try and predict sea ice, okay, forward in time over a grid of points. And this is a well-motivated problem. So you have something called Arctic amplification. So the Arctic, sorry, Arctic, not Antarctic. The Arctic is heating up faster than the rest of the world, and there's a lot of studies at the moment trying to work out why and to work out which geographic regions sort of are contributing to this effect. So some of the problems are that it's very hard to find these regions. Okay, it's a very complex, nonlinear, noisy system. And it's very hard to predict sea ice more than 2 months in advance. So I have this grid of points over which I measure the sea ice. This will form my state space. And then I'm going to take a reproducing kernel Hilbert space corresponding to a polygaussian. So that's a kernel that's a polynomial times a Gaussian. And I'm going to run EDMD. Okay, and if I do that, I get these eigenvalues. So lambda is the eigenvalue. I've shown the logarithm and the argument here to correspond to the time being monthly. Okay, so continuous time system sampled at discrete time points. The color here corresponds to that residual. Okay, so those errors that I can get using that green matrix. Okay, and I can start to pick out the geographic regions corresponding to those Koopman modes. So remember, those are the projections when I expand out my state space. So I get the mean sea ice mode, and then I get sort of this monthly variation, which you're seeing over here. So this is just, of course, melting in the summer and building up over the winter. But I can also, amongst a lot of the spurious eigenvalues, use this residual to pick out some decaying modes. Okay, so the logarithm of the absolute value of lambda is less than 0, which means that these eigenvalues live strictly inside the unit disk. Okay, so they correspond to decaying dynamics, and I can pick them out. Okay, and then what I can do is I can even trim my approximation of the Koopman operator to only those pseudo eigenfunctions with small epsilon, and this allows me to build up an accurate forecasting system. So here we're predicting binary accuracy, a binary classification problem. So that's whether the grid of points is whether a certain grid is covered in ice or not, and we're looking at the accuracy of that forecast. And for lead times, so forecast times greater than 1 month, we're beating sort of classical dynamical system methods, and also in blue here, IceNet. This is this sort of at the time of writing was a state-of-the-art neural network-based model. Okay, so getting the spectral information is actually very useful in practice. It's not just sort of an academic problem of cleaning up these eigenvalues. They actually lead to good forecasts. Okay, so to wrap up, I thought I'd show you sort of four major problems that are driving current research. And these four problems are very much related to what I've been talking about so far. So the common thread is closure in infinite dimensions. So you're going from this infinite dimensional Koopman operator to a finite dimensional representation, and somehow, or truncation, and somehow you want to figure out what do you lose in the process. Can you guide the truncation or correct it by studying that problem? So the first is implementing new tools for continuous spectra and applications. So those are systems where you don't just have eigenvalues and eigenfunctions of the Koopman operator. So these are typical for chaotic dynamics. The second is dictionary learning with guarantees. So can you use error bounds for the spectra and forecasts, for example, to actually tell you how to pick the observables, okay, so those basis functions that form that finite dimensional subspace. The finite dimensional subspace is called a dictionary in the community. Control, okay, can you use residual and subspace invariance to sort of control the closure errors for control? Okay, so you're wanting to drive the system into a certain state or something like that. Can you also do it for non-autonomous systems? So there's the systems that change in time. Now, one way of dealing with non-autonomous systems is to augment the state space. So you view time itself as part of the state space. So this makes the state space a lot bigger. And then, of course, with your snapshots, you have to not only look at the system and how it evolves, but you have to look at for every time point you're dealing with, you also have to have space points as well. So it gets very expensive, and you can't deal you can't with this method deal with scenarios where you only have a single trajectory of data. Okay, so let's sort of unpack these four and give you sort of a brief snapshot of what people are doing and how what it might look like in the future. So we actually have some tools for continuous spectra. So here I've got a glimpse of the main methods that people are working on. So it turns out that if you take the autocorrelations of the dynamical system, they're under certain conditions, they're the Fourier coefficients of something called a spectral measure, which sort of gives you a distribution of how the spectral information of the Koopman operator is distributed over its spectrum. So there's some very nice work. Where's my mouse? Here that's using Fourier filtering to really get these expansions of these measures, because you run into things like Gibbs oscillations. You can also use the resolvent, so that's the shifted inverse of the Koopman operator to attack this, and this gives you generalized eigenfunctions. There are eigenvalue-based methods. So, for example, here there's a method that takes periodic approximations of Koopman operators. You can also, in continuous time, look at the generator. So you now have a semi-group rather than a discrete time dynamical system. And then you compactify either the generator or its resolvent. So there's some papers here. And you can also look at things called resonances. Okay, so these are where you analytically continue the resolvent through the spectrum. And there are actually connections with extended dynamic mode decomposition. And some of those spurious eigenvalues that I was showing you earlier, often they can be connected to these as well. So just here's a picture of what these might look like. So this is the Lorentz system. I'm parameterizing the spectrum, which is the unit circle, by an angle. And here I'm plotting this spectral measure, which in fact, in this case, is continuous. So there are no eigenvalues. There's no delta distributions in this measure. And you can pick out these features. Okay, so we have tools, but at the moment, we don't really know how to integrate these into applied domains. How do you, for example, chop up the continuous spectrum and make it useful for reduced order modeling? So I think this will be an area where people will start to take these tools and build algorithms that actually use them to do various things. So I'm very excited to see where this will go over the next 5 or 10 years. What about dictionary learning? So just give you a very quick example of the type of pipeline that you might use. So in a recent paper, we developed error bounds, both in L2 and RKHS cases, for forecasting systems. So here I'm just going to show you how it looks like for Pluto and its 5 satellites. Here's sort of a picture of the dynamical system. It's a complex chaotic system. I'm going to predict, I think in this case, it's the position or velocity of one of the moons or something. I can't remember exactly. Ask Gustav, the student. And I'm going to apply RKHS error bounds to predict how good is my forecast using the Koopman operator. So over here I have the error bound that you can get. Here I have the exact error bound, and it's very pessimistic. Okay, so we also developed a sort of a Gaussian process method to get an expected error bound. So here you're sort of studying the statistics of these closure issues when you go outside the finite dimensional subspace that you've projected on. Okay, so the question is sort of, can you use this to select the dictionary to get a better, more invariant subspace? And in fact, for this example, we were able to do that using some stochastic gradient descent. But a more sort of general question is what's next? Okay, so we now have these algorithms that can get these spectral properties and these forecast properties. How can you develop pipelines like this that actually tell you how to choose your observables to study these operators? What about control? So here I've got a video, it should start to play, of using the Koopman operator to control a soft robotic arm. Okay, so I'm not really going to go into the details of how this is actually done, but one of the advantages of the Koopman operator being linear is that once you truncate, you can start to use all of the algorithms that people have developed for linear control systems. Okay, so this is a very nice paper in Science Robotics where the authors were able to use Koopman operators to train this robot. So you'll see in an example that it's going to follow a stick. So here we go. Yeah. So they're able to build a finite approximation of how the system behaves when you change the input. Okay, and they're able to train this thing. Now, when you do this, of course, when you truncate to a finite dimensional approximation or linear system, you've again got a non-invariant subspace issue. So that's sort of an open problem. There are results going towards it at the moment, but a general problem that people are very interested in is how do we control design under non-invariant lifted subspaces. Okay, and then finally, non-autonomous systems. So there is work that avoids this augmentation method. Okay, so in this very nice paper, the authors were studying a diffusion maps algorithm to capture systems that change in time. In this case, it's things like sea surface temperature and surface air temperature. Okay, so you see the rise in time, and they were able to actually get approximations of the spectral properties of these non-autonomous systems from a single trajectory. But in general, this is very difficult. Okay, so one of the big problems that people are facing at the moment is how do you build methods that avoid this augmentation and can rely on a single trajectory of data, because this will be really important for things like climate study. Okay, so to wrap up, before I conclude, I just wanted to give sort of two very shameless plugs almost. So the first was mentioned in the introduction. There'll be a book appearing in August on infinite dimensional spectral problems. I've sort of zipped through a couple of stuff in this final chapter here. So if you're interested in any of these areas, then please do talk to me. But this will be out in August, and we'll have lots of classifications in that hierarchy I was describing, algorithms, examples, and exercises as well. So I've been using it as a textbook for the courses here in Cambridge as well. So it's designed to be accessible to graduate students. The second plug is that if you're interested in Koopman operators or operator theory in machine learning and dynamical systems, then we have a program at the Isaac Newton Institute in August. Okay, so the details are here. You can go to their website. So if you want to come or just simply enjoy Cambridge in the summer, it's a beautiful place, then please do get in contact. It'd be a pleasure to have you come and be part of the program. So to summarize, data-driven spectral problems for Koopman operators are hugely popular, but standard truncation methods can fail because you're dealing with an infinite dimensional beast. Okay, so you really need the infinite dimensions to capture true nonlinear effects. And the solution is to go to infinite dimensions. So I gave you a hint at some general methods with convergence for spectral properties of Koopman operators. This led to practical gains in sea ice forecasting. You can also place these into a hierarchy to start to see how difficult these problems are. So you have lower bounds through adversarial dynamical systems, upper bounds through these sort of infinite dimensional algorithms, this green-green matrix in the case of this talk. It's fair to say that we now have a near complete spectral picture for Koopman operators in L2 and RKHS spaces, but still those open problems that I was talking about at the end of this talk are really the next step beyond just spectra. So we have related challenges that are related to these issues and really shaping current research. I think I'll stop there. That's all I wanted to say, but thank you very much for having me and for paying attention.
Yes, thank you, Matthew, for this really lovely, interesting talk. I have a number of questions, but I just wanted to check and see if anybody in the chat would like to ask something first. If not, just post your questions. There. Can you see that, Matthew? If not, I
Uh,
can read it.
I
I can
can't
read.
see. Yeah, that'd be
All right,
great.
I'll read it. It says, this is from Baltasar Befru Lozano, my colleague here at Simula. He asked some questions. He said, practical Koopman methods nowadays rely on learning a latent space where dynamics are approximately linear. Do your spectral approximation guarantees extend to linear to learned
Abs-
representations?
Yeah, absolutely. So all they're actually doing in that case is they're learning a set of observables. So you go into latent space, okay, where the thing is approximately linear. That map you can think of as a collection of observables. So with that interpretation, yeah, exactly, everything follows through. And in fact, um, that's kind of what we're doing here.
Hmm.
Okay, so in this case, we're learning a latent space using kernel methods, but we could have used a neural network or something else entirely. And we're using the error bounds um, from forecasting in this case, not just Spectra, forecasting multiple time steps to train the latent space, and that yields better predictions of the system. So yes, absolutely, it
Hmm.
all carries through to those scenarios.
Hmm. He has more interesting questions, so I'll continue if you don't mind.
Excellent.
He said, I am interested in the notion of representation optimality that minimizes spectral approximation error or forecasting error. Well, yeah.
Yeah. So one way that you can do this, you start off with a uh, oh, uh, yeah, here we go. You start off with a big dictionary, or think of it as like some very large neural network or something. And then you can look at the invariance property of that subspace. And in fact, this is something we do in the paper, is you can develop what we call principal dynamic mode decomposition, or I can't remember the exact, rather embarrassing. I can't remember the exact what it exactly stands for, PAD, which essentially, when you're looking at these systems, it gives you the subspace error between your initial dictionary and one or two or how many time steps forward. And you can look at the directions which are most invariant. And this boils down to a single value decomposition. And then you essentially pick the vectors with the smallest difference, okay, the smallest singular value, and that allows you to build up a subspace of your initial dictionary, which is optimal in terms of the invariance property of the dictionary. So if you start off with a large enough dictionary, you want to trim it down to say, 4 or 5 basis functions. This will give you the best choice. So yeah, if you're interested in that, then have a look at this paper here. And we have lots of examples showing that this will actually beat sort of the standard method, which is to take an SVD of the data matrix, things like POD, that kind of thing, and give you a better approximation in time. Also better spectral properties as well, spectral approximations.
So great. And then another question of his is it possible to provide convergence rates of the approximated spectrum as data size increases? And how do these rates depend on system properties, for example, complexity and
Right.
dimension?
Perfect. Yeah, so let's go back here. So there are two limits here. Now, if you have assumptions on the dynamical system, they'll allow you to get a rate in terms of m, the number of data points. Then you can combine these two limits. Okay, but to do that, you have to study the error of the quadrature here. So for example, there's work. So let's say that you collect the data from a single long trajectory and you weight them equally. What essentially you're doing is you're assuming some form of ergodicity and using the ergodic theorem to prove convergence to this inner product. So what you need to be able to do that is some error rate on ergodic theorems. Now, for certain classes of mixing systems, you can get precisely that, and there's a lot of very nice work, classical work that does this. Um, One of the reasons underlying this impossibility result here is that, in general, unless you have extra assumptions, there's no uniform rate of convergence. Okay, so you have to be a bit careful about the types of systems you allow. You could also, for example, take random sampling here, so some sort of Monte Carlo estimate, and again, you can develop rates. If you're in a small dimensional system and you're free to choose these x points, then if your functions here are regular enough, so notice here that it's not just the dictionary, but k of the basis functions. So remember, composing with the function f, if that's regular enough, you can develop rates. So if I go to this classification result here, if I assume my system is measure preserving and I can control how regular f is, I can build up a convergence rate thing for the quadrature. And that allows me to avoid needing two limits. So that's why I live down here in this classification here, which is a single limit with error control. So yes, sort of the way that you sort of study the amount of data and how much you need is very important for developing optimal algorithms and figuring out how many limits you need. In general, I would say that the error analysis for large M is a lot easier than for large N. Okay, it's very hard to get error rates. For example, if we go over here, where you only need a single limit, it's in general impossible to get a rate of convergence here. So this is why having error control of this form is very important, because you know that whatever you've computed in finite time is reliable. You just don't know whether you've got all of the spectrum yet, or all of the spectral properties. So hopefully that goes some way to sort of answer some of that question.
Great. I assume it does. He hasn't said yes or no, but I'll ask him tomorrow when I see him. He said thanks. So I'm guessing yes. I had some really basic question because this is a bit outside of my field, but you said earlier about the choice of the psi j, and in one of the examples you said, "Oh, we choose radial basis functions." Um, yeah, I guess it was here, but I mean in general. So how do I choose these
There's
functions?
no,
Yeah.
I mean, so this is one of the reasons dictionary learning is so important. It's really an art form at the moment. There's
Mm,
a sort of hard and fast rule. What typically works well in practice when I'm stuck is to do something called delay embedding. So that's essentially where you're looking at staggered time series backwards in time. All it is really is a Krylov subspace approximation of the Koopman operator. So you augment the state space with, one time step backwards or two and so on to get a larger state space. And then you hit it with a kernel method. So you're combining a Krylov subspace method and then you're doing a kernel method on top of that.
mhm.
So in fact, although I didn't go into the details, that's what I was doing in this case. It's sort of a Krylov subspace method and then a kernel. And of course, what you really want to know is whether your dictionary is doing a good job or not. And that's really why these error bounds are important, because although you might not have any guarantee before you try it that the dictionary is going to work, once you get errors, you know that you're doing a good job.
Mm.
Um, so yeah, really at the moment it's you have to play around a lot, but Krylov plus uh, kernel methods is the way to go, I think.
Mm. And if you go back to when you introduced EDMD and DMD, I understood a bit before this, there was a formula for the Koopman operator using, yeah, these matrices.
Yeah.
So you form these matrices and you said, okay, this is Koopman. And that I get, and I thought that the psi x and the capital psi x and the capital psi y were your sort of blue and green matrices. And I guess you use those to build this finite dimensional approximation of the
Hmm.
operator K. But then where do you use the green one in
Oh,
this
sorry.
formula?
Yeah. Let
Yeah.
me. That's not used in EDMD.
Ah, okay.
So you use the same data as EDMD, so you don't need any extra data to form this additional matrix. I'm
Yeah.
going to call this gram matrix G, this matrix with 1K, K1, this matrix with 2K2.
Mm.
Then it appears when I want to post-process or compute residuals. So if I go through here, you see it appearing here.
Uh-huh.
So there's a non-linear dependence on the spectral parameter here. And that's really important because that this K2 is capturing, if you're thinking about sort of taking a truncation of this infinite matrix, it's looking at the column space that you've missed when you truncate. It's looking at how your finite approximation interacts with the stuff that you miss during truncation, which is why sort of it's good to think of it as correlation forward in time.
Okay, it's interesting. So basically, the construction of the Koopman operator is the same as EEDMD, correct?
Exactly.
But
Yeah.
this is just for to get the error bound. You introduce this additional
Yeah. And then
matrix
if
here.
you want to, so there's no guarantee that the spectrum of EDMD will actually uh, well, it can do two things that are bad. You get spurious eigenvalues. So we saw that here. It can
Yeah,
also miss regions of the spectrum. So if we go here, we're missing all of the spectrum.
the whole thing. Yeah.
So that's why you need often an additional thing as well. So let's go here. Here, I'm not just cleaning up, eigenvalues of EDMD. I'm specifically searching for these pseudo eigenfunctions. And I can prove that when I do this, I don't miss anything.
Mm,
Okay, so it's once you've got this sort of function of lambda and g, you can do various things with it to hunt for the spectrum, and this is one example.
mm. Okay. And another thing you mentioned in passing, and maybe I misunderstood, but you said something about how the impossibility theorem on I guess it was in the previous slide, how that somehow has implications for things like randomized algorithms and optimization. You mentioned stochastic gradient descent,
Right.
for example. So what did you mean by that?
So you can replace this statement here, deterministic algorithms, by randomized algorithms, and by that I mean algorithms that can flip coins,
Hmm.
and they're free to do whatever they want. So they could use, that random sequence of coin flips to decide where in the disk to sample points. That would be random sampling of trajectories, or they could use that to, train a neural network with stochastic gradient descent to, search for a dictionary or something like that. So there's really, because of the way the proof works, um, there's no constraints on the type of algorithm allowed. And then the result is that you don't get convergence here with probability greater than 1/2. So you can't do better than just random coin flips.
Mm, okay. So that is extreme. I mean, how does this, you said ask me about the proof. Maybe you could sketch it in just a few minutes. Obviously, we don't really have that much time left,
Yeah, of
but we
course.
start a few minutes late.
I dropped a hint hoping someone would ask, of course.
Yeah.
Uh, Here we go. So I'll do the deterministic case because it's a bit easier.
Hmm.
So, what did I do there? Yeah. So you always want to get a phase transition. So here I'm going to start off with, remember I'm on the disk,
Hmm.
rotation by pi, the spectrum of this Koopman operator is plus or minus one. And then there's this lemma, which is can be found in a very old paper here. So what I do is I take two sets of data, x and y, so the distinct points in an annulus inside my disk. Okay. Then there
Hmm.
exists a measure preserving homeomorphism H that acts as the identity of this annulus, and such that if I take H of X and then rotate by pi according to F naught, I get H of Y. So if you imagine taking the inverse of H over here, it's telling me that I've sort of got conjugacy between my dynamical system, at least on the level of these data points. So I'm studying the map that goes from X to Y, and via this homomorphism, I can think of it as behaving in a similar fashion to the rotation. So we're going to use this lemma to trick algorithms. So here's the proof. You suppose for a contradiction, a sequence exists for all f in your class. And now, once I've assumed this, I'm going to build an adversarial f to break this convergence. So I'm going to start off with a slight perturbation of rotation by pi. So this is just in um, polar coordinates. I've got this bump function. It's not too
Hmm.
hard to show the spectrum of this is the whole circle. So now I converge by assumption over here. So there exists some finite n1 so that the distance of I to the output is bounded above by 1. And that's because, of course, I is inside the circle. So it's inside the spectrum. So now I'm going to use the fact that gamma n1 can only sample a finite number of times. I don't need to know where it samples. It could do it adaptively or however it wanted. I just know it's finite to output this set. And I pick my x and y in my phase transition lemma to correspond to these snapshots. So I can change f1 tilde to f1 via this homeomorphism. The
Hmm.
data is consistent because x maps to y, at least on those 5 data points under this conjugacy. So I have to, because I'm deterministic, I have to behave in the same way. So this inequality has to hold when my algorithm is applied to F1. Now, the problem is the spectrum of this F1, so this measure preserving homeomorphism induces a unitary um, transformation of Koopman operators. So the spectrum is just the same as the spectrum
Oh,
of rotation, which is plus or minus one. So that's
okay.
going to break this, right? So
Yeah.
remember, I proved there's no sequence of algorithms. So all I have to do is apply this algorithm successively on a cascade of annuli
Hmm.
going to the origin. I can do this because they're the identity, these homeomorphisms are the identity of the annuli. So once I've gone beyond a certain region, I'm consistent. This limit exists, okay, the consistent data and everything. But this means that the distance of I to gamma and k of f, this limit is less than or equal to 1, but the spectrum of this is plus or minus 1, so it's a contradiction. So you've got this sort of phase transition where you're tricking the algorithm by changing the dynamical system, which perturbs the Koopman spectra.
Okay.
So yeah,
Yes,
that gives you an idea. So really
it gives me an idea. Yeah.
the important thing is the order. So you first suppose a sequence exists,
Right.
and then your goal is to build an adversary that somehow breaks it.
Okay.
So there's
Okay.
nothing here. N is just an index. It's not, data or size or anything like that. Any algorithm you can think of, like EDMD, would give you such a sequence, right?
Mm,
But it's,
mm.
it's somehow easier to run the proof if you abstract away and don't think about data or dictionaries.
I see. I see. Wow. Okay. Thank you. Um, Good. I think we ran out of time, but I had one last question. So, you may have heard of these things called Fourier or neural operators, right?
Mm.
Which are sort of an infinite dimensional operator that, as far as I recall, I might be misrepresenting this, will take a function, so an infinite dimensional object, and on the one hand, it will do an algebraic transformation of that, really algebraic in the sense of like maybe I multiply it by some kind of matrix and add a vector to it. On the other hand, it will do a Fourier transformation of it. And then these things are run sort of in serial together to give you the representation of some kind of infinite dimensional operator, maybe the solution operator for a PD or something like that.
Yeah.
To make these things practical, at some point they truncate these operators on the inside. And I'm wondering if you ever thought about these things and if the same kind of error that you see here in Koopman perhaps would be present there as well. I
So
realize, yeah.
I've sort of thought about thinking about these things, if that makes sense, but I've
Yes.
not sort of like sat down and done it yet. Absolutely. In fact, this is one of the areas that I'm wanting to move into next is seeing how this sort of study of infinite dimensions to finite dimensions interacts with some of those types of methods. So I don't really have an answer at the moment, other
Mm,
than I would expect similar phenomena, but it might behave differently. Somehow the spectrum of an operator is quite a brittle object, as you can see here, right? You add the small
yeah.
perturbation, suddenly changes. There are lots of things people are interested in that are more stable, like forecasting. So if we go back to this pseudo eigenfunction thing, although it's hard to get the spectrum, often it's a lot easier to get approximations like this,
Yeah.
which give you sort of like a good approximation of a finite time horizon.
Mm,
Um, so you can think of that, in terms of operator theory, is there are different forms of convergence. You can have what's called strong operator convergence, which
mm,
is where your approximations applied to a vector converge to
mm,
the operator acting on the vector. And that's a lot weaker than spectral properties converging.
mm.
So I'd expect a lot of the properties people are studying for these Fourier neural operators to be more stable than the spectrum.
I
Um,
see.
yeah.
Mm, great. Okay. Thank you so much, Matthew. This was very intriguing, and I hope everyone else who joined us found the same. Yeah, and that's it for today. So
Thank you. Thank you for
have a
having me.
great afternoon. See you
Yeah,
soon,
you too.
hopefully. Alrighty. Bye bye.
Bye bye.